4.5 billion years ago, something the approximate mass of Mars hit the Earth at roughly 45 degrees. The collision lasted less than 24 hours. The impactor did not bounce, it did not pass through, it was absorbed, partially, and the debris that was flung into orbit was so hot that most of it was vapor. Not dust, vapor. A ring of silicate gas and molten rock settled into orbit around what remained of the proto-Earth, and within perhaps 100 million years, fast by planetary standards, it had coalesced into a single body. That body is the Moon. This is not mythology. It is the current scientific consensus, supported by 4 separate lines of physical evidence, and it carries one implication that the textbooks tend to understate. This event almost certainly happened exactly once. The geometry, the mass ratio, the angle, the timing, all of it sat inside a window so narrow that every other terrestrial planet in the solar system missed it entirely. Mars has 2 moons. They are captured asteroids, small, irregular, dark, nothing like our moon. Venus has no moon. Mercury has no moon. The moon is not a standard outcome of planetary formation. It is an anomaly, and anomalies in physics are not decoration. They are evidence. The moon is the wrong size. Not wrong in the sense of aesthetically surprising. Wrong in the sense that no accepted model of planetary formation prior to 1975 could explain how a planet the size of Earth acquired a satellite that is roughly 1/81st its mass. That ratio is exceptional. Jupiter's largest moon, Ganymede, is enormous in absolute terms, larger than Mercury, but its mass is less than 1/10,000th of Jupiter's. The mass ratio of the Earth-Moon system is the largest in the solar system for any planet-moon pair. The composition is also wrong, in a specific and telling way. The Moon's density is significantly lower than Earth's. It is depleted in iron. The Earth's core is iron, dense, heavy, sunken to the center by gravity during the early differentiation of the planet. The Moon has almost no comparable iron core. Whatever the Moon is made of, it is not a representative sample of the early Earth. It is missing the heavy elements. And then there is the orbit. The Moon orbits in almost the same plane as Earth's equator, which is also almost the same plane as Earth's orbit around the Sun. This is not what you would expect from a randomly captured body. Captured moons, when they exist, tend toward irregular orbits, tilted, eccentric, sometimes retrograde. The Moon's orbit is almost suspiciously clean. In the 1960s, 3 competing hypotheses existed. The first was fission, that the early Earth was spinning so fast that a blob of material broke off from the equator and became the Moon. The second was co-accretion, that the Earth and Moon formed simultaneously from the same disk of material. The third was capture, that the Moon formed elsewhere and was gravitationally caught by the Earth. Each of these models explained some of the data. Each of them failed on the rest. Fission required an Earth rotating so rapidly that the angular momentum numbers don't work. Co-accretion couldn't explain the composition differences. Capture couldn't explain the orbital geometry. By 1970, the Apollo missions had returned samples from the lunar surface, and instead of settling the question, they made it harder. The samples came back, and geologists did what geologists do. They measured everything. The oxygen isotope ratios were the first shock. Oxygen comes in several isotopic forms, different numbers of neutrons, same element, and the ratio of these forms varies depending on where in the solar system material formed. Rocky bodies that formed close to the Sun have different isotopic signatures than bodies that formed farther out. This is a reliable chemical fingerprint. The Moon's oxygen isotope ratio is almost identical to Earth's, not similar. Almost identical, to a precision that no other pair of solar system bodies matches. The Moon and Earth appear to be made of the same reservoir of material, which immediately ruled out any model where the Moon formed somewhere else and was later captured. A moon that formed in a different part of the solar system would carry a different isotopic signature. The capture hypothesis was finished. But co-accretion had the same problem in reverse. If they formed from the same disk, why is the composition different? Why is the moon depleted in iron and volatile elements, water, carbon compounds, the light stuff, while Earth retained them? Objects forming from the same disk should be more similar, not less. Fission failed on angular momentum. The numbers simply don't add up. You cannot spin a planet fast enough to eject a moon-sized blob and still arrive at the current Earth-Moon system. The energy isn't there. All three hypotheses had been tested against the best physical evidence humanity had ever collected from another world. All three had failed. The Apollo program had solved a great deal. The origin of the moon was not among the things it solved. In the summer of 1974, William Hartmann sat in a conference room in Nice and listened to presentations about the outer planets. He was not taking notes on what the speakers were saying. He was staring at a problem that had been accumulating in his mind for years: the late-stage disk, the cloud of planetesimals that had built the terrestrial planets, should have contained dozens of Mars-sized bodies. The 4 planets that existed were not enough to account for all of them. He wanted to know where the rest had gone. I cannot locate the exact line where the physics stops being improbable and starts being impossible. And that threshold is what this particular event keeps forcing me back to. The window required to produce the moon is not just narrow. It is narrow in 4 dimensions simultaneously: mass, angle, velocity, and timing in planetary formation. Shift any single variable significantly, and you get a merged planet, a destroyed planet, or silence where the moon should be. The accident had to be almost exactly the accident it was. Hartmann was a planetary scientist at the Planetary Science Institute in Tucson. He had spent the previous several years working on the physics of impact cratering. What happens to rock and metal when something very large hits something very large? And the question from Nice had not left him when he returned to his office. The solar system had produced 4 terrestrial planets. The late-stage disk should have contained many more Mars-sized bodies. Where did they go? The answer, he suspected, was that they hit things. In 1975, Hartmann and his colleague Donald Davis published a paper in the journal Icarus. Davis had been working independently on the same problem from a different angle. He had been calculating the probable size distribution of late-stage impactors, and the numbers kept pointing toward objects large enough to reshape whatever they hit. The two of them had arrived at the same place by different roads, and in their Tucson office they spent several weeks checking each other's calculations before they trusted the result. The paper proposed that the moon formed from the debris of a collision between the early Earth and a Mars-sized planetesimal. The impact would have been at a glancing angle. The impactor's iron core would have merged with Earth's. The outer silicate layers of both bodies, the mantles, the lighter rock, would have been vaporized and ejected into orbit. The moon would have condensed from that ejecta. This explained the iron depletion. The moon formed from mantle material, not from core material. That's why the density is low. It explained the oxygen isotope match. If this planetesimal, which would later be named Theia, formed in roughly the same part of the solar system as Earth, it would carry a similar isotopic signature. 2 bodies from the same neighborhood of the disk would share a chemical fingerprint. It explained the angular momentum of the Earth-Moon system, which is unusually high, consistent with a large oblique impact. And it explained the depletion in volatiles. The impact was so energetic that it drove off the water and light compounds, and the moon condensed from what remained. The hypothesis gained traction slowly. By the time of a conference in Kona, Hawaii in 1984, where planetary scientists gathered specifically to evaluate it, it had become the leading model. The Apollo samples were reanalyzed with the new framework in mind: the evidence fit. But fit is not the same as confirmed. The oxygen isotope match, which seemed to confirm a common origin, became a puzzle of a different kind. If Theia formed in a different orbital zone, even slightly different, its isotopic signature would be slightly different from Earth's. But the Moon and Earth are not just similar in oxygen isotopes, they are nearly indistinguishable. In 2012, Junjun Zhang stood at a mass spectrometer at the University of Chicago and ran titanium isotope measurements on lunar samples collected during the Apollo missions. The signatures were so close that Zhang and her colleagues could not separate them with the instruments available. Earth and Moon, by titanium isotope ratio, are the same object, which should be impossible if Theia was a distinct body from a different orbital path. Some researchers began to argue Theia must have been isotopically identical to Earth, which strains credulity unless Theia formed in almost exactly the same orbital region, which is dynamically unusual. Others argued the impact was so violent that the disk was thoroughly mixed before the Moon condensed, erasing any isotopic difference that might have existed. The two explanations make different predictions about the Moon's interior, and we do not yet have the measurements to distinguish between them. Robin Canup was sitting in front of a workstation at the Southwest Research Institute in Boulder on the night her first clean simulation ran to completion. She had been building impact models for several years, running the collision through thousands of numerical variations, changing the mass ratio, the angle, the velocity, looking for the configuration that produced a moon-sized body in a moon-like orbit. In 2001, she found one, a specific impactor mass, a specific angle. In 2012, she came back to the same problem with faster computers and found a different solution, a larger impactor, hitting a larger proto-Earth at higher velocity, producing a more thoroughly mixed debris disk. Both simulations produce the Moon. They do not produce the same Moon by the same mechanism. The simulations are now detailed enough to track individual parcels of material as they travel through the impact. They are not detailed enough to tell us which version of the impact actually happened. The Moon exists. The isotopes match. Beyond that, the model has several internally consistent versions, and the data required to choose between them does not yet exist. The collision set Earth's axial tilt, the obliquity, at roughly 23.5 degrees. The axial tilt is what produces seasons. A planet with zero obliquity has no seasons. The poles are perpetually cold, the equator is perpetually hot, and the distribution of temperature across the surface is static. A planet with very high obliquity has extreme seasons. The poles alternate between months of constant sunlight and months of permanent darkness. 23.5 degrees sits in between. It allows equatorial regions to cool and polar regions to warm, driving atmospheric circulation, ocean currents, and the cycling of nutrients that make soil productive across a wide range of latitudes. But the tilt itself would be unstable without the Moon. In 1993, Jack Wisdom ran a simulation at the Massachusetts Institute of Technology that most people in the field remember not for its elegance, but for what it showed when he removed the Moon from the model entirely. Without the Moon's gravitational stabilizing influence, Earth's axial tilt varies chaotically, swinging between near zero and roughly 85 degrees over millions of years. The Sahara and the Arctic would trade places repeatedly. The conditions for complex life to establish itself across geological time would not hold. The Moon is not just a passenger in Earth's orbit, it is a gyroscope for the planet's rotation axis. The early Moon formed much closer to Earth, perhaps at 1/10 the current distance. At that range, tidal forces were enormous. They acted as a brake on Earth's rotation. The early Earth was spinning with a day perhaps 6 hours long. The tidal friction from the Moon gradually transferred angular momentum from Earth's spin to the Moon's orbit, slowing the planet's rotation and pushing the Moon outward, where it continues to drift at roughly 3.5 centimeters per year. A 6-hour day produces different atmospheric circulation, different heat distribution across the surface, more violent weather patterns. The tidal engine didn't just slow the planet, it stabilized the conditions at the surface. Every other terrestrial planet in the solar system went through the same disk, the same late-stage bombardment, the same rain of planetesimals. Mars got 2 small captured rocks. Venus got nothing. Mercury got nothing. The difference is not in the process. The process was universal. The difference is in what happened to land, or not land, on each of them at the specific moment in their formation when such an impact would have been constructive rather than destructive. Too early and the planet isn't differentiated enough. Too late and the debris doesn't coalesce cleanly. The window is real, and most planets went through it without the right collision happening inside it. The night I understood what the tidal engine actually did to early Earth, that it slowed the planet's rotation from a 6-hour day to a 24-hour one, and that this specific deceleration was the difference between a planet with stable surface chemistry and one without it, I stopped being able to look at the moon as background. It is not scenery. It is the mechanism by which this planet became a place where anything could persist long enough to grow complicated. We have one example of this outcome: Earth. We have 0 confirmed examples of Earth-like planets with large stabilizing moons elsewhere. The exoplanet surveys that have detected thousands of planets beyond this solar system are not yet sensitive to moons at the scale and distance required to confirm them. The question of whether the giant impact is rare or common is genuinely open. The model suggests it is rare. The simulations indicate that the specific conditions for a moon-forming impact are not the default outcome of planetary formation. They are one outcome among many, most of which produce no large moon or produce a moon that is subsequently lost. But we have run the experiment exactly once, and we are the result. Sometime in the late 1990s, a geologist named John Valley sat in a clean room at the University of Wisconsin and began analyzing a fragment of zircon crystal, a mineral that survives almost everything, recovered from ancient Australian rock. The crystal was 4.4 billion years old. It was older than the oceans, older than any known continent. It was, at the time, the oldest solid material on Earth that anyone had measured. Valley held it between 2 fingers and thought about what it had survived: the Hadean Eon, the period immediately after the moon-forming impact, when the surface of the Earth was still partially molten and the sky was opaque with ejecta. The crystal had been there. It had recorded the temperature of its formation in its chemistry. The temperature was not the temperature of a hellish, lifeless furnace. It was the temperature of liquid water. 4.5 billion years ago, something hit the Earth. The moon is the scar, and the scar is the only reason you are here to see it.